So when we left off, I think I was just introducing radical polymerization. This is one of the most common uses of free radical chain reactions to form polymers. So you'll remember that polymerization joins individual monomer units into a long chain. I always think of those toys that we had when we were babies. Just to show you, I always think of these beads. I'm the middle child in my family. I had a younger sister, so I remember her playing with these snap together beads. I always think of these when I think of forming polymers. That each shape is a monomer, and if you had only yellow shapes, then you would have only that monomer unit. So say these were ethylene, then you could make a long chain of only ethylene monomers, and it would be polyethylene. What's shown here is many different kinds of individual monomers in the analogy that I'm using. So if ethylene is our monomer, we can, through a free radical chain reaction, we can polymerize and form a long polyethylene chain up to n number of monomers. This could be 10, this could be 10,000, this could be 100,000 monomer units to form a polymer. In our radical polymerization step, we begin with initiation. We're going to have some type of initiator, and we're going to create in this case, two alkoxy radicals. One of those is going to add to a alkene and give us the alkyl radical, and then that will go on in the propagation step to add to another monomer unit, generating yet another consuming and generating a propagation step radical, and this addition can continue as long as we have monomer available to make a very long polymer. So this gives us the overall net reaction. The termination of that polymer chain can occur through a couple of different ways. In a radical mechanism, we have the alkoxy radical coupling with our alkyl radical to terminate with an alkoxy group on the end. We can have two alkyl radical chains joining and coupling to give a longer chain, combination of chains. So in this reaction mixture, chain branching is inevitable. We have a alkyl radical abstracting a hydrogen and generating a radical in the chain, and then this can add to a monomer unit and begin a chain branch. And this may terminate quickly, or it may grow to be quite long. Highly branched polyethylene forms flexible polyethylene polymers. So like our polyethylene squeeze bottles in the laboratory. Unbranched polyethylene is going to be brittle and rigid, like a bottle cap, is an example here. There are derivatives of that ethylene monomer that also can form different polymers. So if we have propylene rather than ethylene, so we have a methyl substituted ethylene monomer, then we can form polypropylene. And polypropylene is commonly used in carpet fibers, car tires. Polypropylene can be used in piping in the same way that PVC piping is used to remove wastewater. If we have a phenyl substituted ethylene monomer, then we have a styrene monomer, and we can form polystyrene. So polystyrene will give us a rigid, hard polymer. Typically, you see this on the cases of televisions and radios. And if we foam the polystyrene, we can get styrofoam, which has very different properties than polystyrene. Chlorine substituted ethylene monomer is vinyl chloride, and polymerizing this gives us PVC. You're probably quite familiar with the white PVC pipe that's used for waste lines and irrigation, lots of plumbing, compact discs, not so common anymore, garden hoses, raincoats, shower curtains, lots of different materials, from quite rigid like piping to quite pliable like a shower curtain. There are different additives in the polymer that will give it these properties, plasticizers. If we have a fully fluorinated ethylene unit, so we have tetrafluoroethylene, and we polymerize that, it's known as under the the trade name Teflon. This is used as a non-stick coating for frying pans. Tetrafluoroethylene has a number of uses. Backing up for a second, we may get into the polymer chapter at the end of the semester. We may not, but I'll mention that if we have a propyl group, a butyl group, the difference between a C4 and a C5 carbon chain is something that we can control, we can produce. When we get to very long polymers, if we have 10,000 monomer units or 100,000 monomer units, we can't really control 100,000 monomer units from 100,001 monomer units. So when we do polymer reactions, when we talk about the number of monomer units, we're talking about an average number. And there is a distribution in the molecular weight of a polymer or the number of monomer units. There is some central tendency, some average number. There'll be some normally distributed amount. There'll be some central tendency, and then there'll be three standard deviations out to the edge of the distribution. So the whole distribution will cover 6 sigma. But we don't have a pure material when we say we have a high molecular weight polymer. We have a polymer that on average has that molecular weight and has a distribution. And we may be able to control how wide the distribution is, but we can't get to what you would call a monodisperse high molecular weight polymer, a polymer that's uniformly every molecule is the same molecular weight. So I'll just mention that